Hello everyone, welcome to this course of Chemical Crystallography by Professor Anshuman Chaudhary from ISER Mohali. This course was started on 25th of July this year, and the end date is the 14th of October. So I am the course TM, and for the live session of this course, it is every Saturday from 3 to 4 p.m. where this is the Google Meet link. So if you have at any point of time any question regarding any part of the video of the professor or any other in general question related to this chemical crystallography course, so please ask your questions in this Ask a Question tab in the SWAYAM portal. So by now I hope all of you are very much familiar with this SWAYAM portal. So here you have all these tabs like announcements about the course, Ask a Question, Progress, Mentor and everything. So in this Ask a Question tab here you can ask a question via mail, and then all of the students can see the question, and then when the question is answered by any core member, then all of you will be able to see the answer, and then also if you had that question, you will get the answer, right? So sorry. So welcome to this session 10 of week 10 of this course. So today what we are going to do, so we are going to discuss the questions and answers related to assignment 8, which was due on the 21st of September. So before we go into that, so a quick recap. So what we learned last week was a very important concept called as a structure factor, and the structure factor is nothing but a mathematical description of how a material scatters incident radiation, and we have learned that it is only valid for systems with long range positional order. And in the structure factor equation, so the structure factor amplitude the structure factor amplitude of the beam which is diffracted by h-scale planes of the crystal. So why are we talking about h-scale planes of the crystal? Because according to Bragg's law, so we can think of a crystal as infinite number of planes of different h, k and l values, right? So this is the structure factor equation, and then this structure factor can be related to what? The structure factor can be related to the electron density, right? So this is what we have learned, that the structure factor is related to the electron density by a Fourier transform. So this is a very important concept because this is the basis which is used in structured solution programs and everywhere, that this Fourier transform which relates the structure factor and the electron density, right? So then here we talked about how this structure factor is a vector, right? And then if it is a vector, then it can be written in terms of its amplitude and then the phase. And what is the phase? So phase is the so this is the vector. It is actually a vector, so no sign is given, but this is the vector where this part is the amplitude and this part is the phase. And what happens is, so as we have now have the basic idea that this phase information actually gets lost, because in the diffraction space it is asymptotic and we lose the origin, and here it means when we lose the exact origin, so we lose the phase information. So that is all. So this was just a quick recap of the structure factor part. So we will now come to this the question answers of this assignment 8, which was due on the 21st of September of this month. So the sorry so the first question was that the packages which are used for structure solution and refinement are Shell XT and Shell XS respectively. So this is false. So why this is false? So you can understand. So if I try to solve any data, okay, so let me try to solve any data. So you can see here, right? So we will come to this part. So I will give you a brief idea about what this all these folders are. So before that, if you see in the solve program, we have this Shell XS and Shell XT, both are in the solve, and for refine we have Shell XL, right? So refine the program which is used for refining, it means in the Shell X package, the program which is used for refining is Shell XL, and Shell XS and Shell XT are both used for solving. So in the question you can see it is given that the package is used for structure solution and is Shell XT and refinement is Shell XS. Hence the overall this is false, because for refinement we do not use Shell XT and Shell XS. What we use is Shell XL, and Shell XS and Shell XT both are used for structure solution. So this is why this will be false. This is why this will be false. So then this next question, so this addition of hydrogens do not have significant impact on R factor. So this is also false, because this is actually a very general concept, because when we have a structure yearly, for example, assume that you have a structure like benzoic acid. So we have a total there are 5 aromatic hydrogens, and for the carboxylate group there is 1 hydrogen, right? So hydrogens also correspond to electron densities. So as long as we do not do that as add hydrogen option, so there are electron densities which are remaining unfulfilled, and there will be a great amount of mismatch between the obtained model and the structural model. Hence when we do the add hydrogens, we can see for ourselves that there is a significant impact on the R factor, in the sense that the R factor decreases significantly when we add the hydrogens and fill up the electron densities. Hence this is also false. So the third question was that the highest cubics represent atoms in your structure which are not assigned during the structure solution phase. So this is also true. This is also a very general thing, so there is nothing to discuss about it. So then in the next question, so in the following image, so this is representing 2 cubics, so Q1. So I hope all of you can see which one is Q1. So this is Q1. Q1 corresponds to a large unsigned electron density, while Q17 arises from a very low unassigned electron density. This is Q17. So you can see this is so much brighter, right, than the other one. So if we do that in OLED, so we can clearly understand this factor that the electron density which is more or large, so that will have brighter color compared to this. So these represents if like for example hydrogens or something which are very lighter elements, or in other words very low electron density. So this is this alert. This is a very common typical alert if you forget to add inversion symmetry to your structure. This is actually a very important alert. If we talk about the other things, so this crystal dimension missing, that is when we go for in OLEX 2, when we are using OLEX 2 for solving, and we go for the report, then if the crystal dimension is missing, it will give us an alert like where it will contain the name, something like that, the crystal dimension missing, then small cc distance, and then poor data to parameter ratio. So all these are also alerts while solving the structure. However, this sim detects new pseudosymmetry. So when this is there, more often than not, it means that you have missed some symmetry element, so which is a inversion center. Okay, so be very careful when you are like seeing this alert, and most of the times it is correct, and you have forgotten to incorporate the symmetry element. Okay. So then we come to the next question. So this is also a very easy question. The question says that the file type which should be opened using Chrysalis Pro for single crystal data handling, that is indexing, data reduction, etc. is, so it should be .bar. So I want to show you our data. Okay, so this is like the name of the data. Okay, so this is IG01 and then 100K. This means that this was taken at 100 Kelvin. So this whole folder is the single crystal data file, and sorry. So if you want to see the first file size, you can see that it is 1.24 GB. This whole file is 1.24 GB. And then when you open it, then you can see there are many folders here and also many files over here. So the professor has taught you that about all these files, file types, how to open them at first in so he has shown you both, right? He has shown you the how to handle it in Broker and also in the Riga Pro, and then using Chrysalis Pro, and then OLEX 2 and everything. So we have to go through that very nicely. So this is just another kind of demonstration that if you open the single crystal file, the total folder is like more than a GB, 1 GB. And then we have different folders. So here in this frames folder, so these are all the frames with this ROTHYPIX, this extension. Okay, so these are the frames which are used for data deduction. So you can see there are so many frames here. Then we have all these folders where all these file names might not make sense to us. So all the file types might not make sense to us, but they are all very important and needed. You cannot delete any of them. Then we have this folder called the movie folder. You can see the size. This is 2 MB. Out of 1 GB, this movie folder is 2 MB. And here what it contains? It contains the image. So this is the image which was taken like before the actual data collection starts, and this is used, why this is used for phase indexing. So I want to index the phases, this phase and the major phase and the side phases or the minor phases, and the top and the bottom phases. If I want to index them, what are the HKL of that, then we have to use these frames. That is why it is very necessary to use a very good crystal for data collection, so that we can do the phase indexing later. So we got to this movie folder. So then there is this temp folders which contains all the temporary files, and then we have this struct folder. So what happens is, if you take a raw data, then you can actually solve it different number of times. You can first solve it using some name, and then you can solve it again for the second time and the third time. So we usually do this because we can vary some parameters and then see that how it is affecting my data. For example, if when you do a structure and you see that there are a 6000 peaks, okay, and you see that it has indexed 4000 peaks, and there are 2000 peaks which are it is showing as wrong peaks. So at first I can do with by excluding the wrong peaks and then going for data reduction, and then second time I can solve it again with including the wrong peaks, right? That is why we can do it multiple times. And if it is actually a twin structure, then by including the, if we solve it with including the wrong peaks, then it actually leads to a better structure. So this has happened to me, and this happens. So this AutoChem or something, they cannot really solve twin structures, and it will show as wrong peaks. But then if you turn on the automatic twin finding, then you can understand that what is the twin law between them and everything. So if you want to solve a structure multiple times, then in the struct folder all of them get saved. So you can see all this. So in the struct folder also there is a temp folder containing the temporary files, which are the last files, but that is not important. So you can see, so I have solved it once, twice, thrice. So all the 3 files are here. Then so we talked about the struct folder, we talked about the temp folder. Now after that we come to the files. So here you can see there will be this Chrysalis Pro, this 16 kb.par file. So that file actually opens in Chrysalis Pro. Okay, so here if you see, so this is the name of the folder or my data, right? So you can see one file. So you can see one file with this name, and then another file with the same name but with a pre in front of it. So for data, when we are doing the data reduction, we will not use the pre file. So this is actually what? This is actually the pre-experiment file. So we don't use that, we will use the original name file. And then we have this INS, HKL and everything we generate. So this GRL file, P4B, so everything, so sir has taught you, so you can go through that videos, right? So in the question that the file type which should be opened using Chrysalis Pro for single crystal data handling, like indexing, data reduction, is the .par file. Okay, so the answer will be the .par file. Then which among the following files contains the experimental structure factor information will be the .hkl file, which opens in OLX 2 mainly. So then this question, so this is a very interesting question, that if a crystal structure indicates fractional value for Z prime, then what does it mean? So it happens for a very higher symmetry molecules, like for example, if you can have like trichlorobenzene or trimethylbenzene, something like that, and then there the there is some symmetry element like a mirror, for example, actually passes through the molecule. Then what happens is we get z prime which is equal to 0.5, because if we go for the symmetry element, then it completes the other part of the molecule. So if a crystal structure shows a z prime equal to 0.5, it means that some symmetry element of the crystal structure is passing through the molecule. It also happens for high symmetry molecule and high symmetry crystal structures, like for example urea. You can search for the crystal structures of urea and you can see for yourself. In most cases, the z prime value for urea is 0.25. So then the next question is which among the following is used to view the molecule and packing of molecules? So the answer is mercury. So I can do this is saccharine, and this is the interface of this mercury software. So when we open this mercury software, so you can I'm just clicking my left mouse and I'm moving it in this kind of three-dimensional space kind of thing. So here you can see, so if at first it shows the space group here, and it shows that it is open in the software mercury. And if here if you go to more information and then go to structure information, okay, I'm showing it to you once again. More infrastructure information, it will give you the formula, and most of the times it also gives you the compound name and everything, but most important is the space group, the cell parameters. Here you can see this for this saccharine. So saccharine means there is one sulfur atom, there is two, which is the sulfur atom is connected to oxygen atom, there is one NH, another carbonyl, and then one benzene ring. The cell length is 9.46, 6.92, and then 11.7. So this means A not equal to B not equal to C. If we look at the cell angles, 90, 100 and 390, which means this is a monoclinic system where my Z is equal to 4, which means there are 4 molecules in unit cell, and Z prime equal to 1 when there is 1 molecule in the asymmetric unit. We can see the R factor when it was solved, which is 3.1%, which is very good. And then we can see all the other informations also, like these atoms, bonds, contacts, and everything. So if you go to symmetry here, you can see the symmetry operations, right? So this is one more monoclinic system. So if we take this XYZ, then if we can apply a two-fold screw axis, and where it is this inversion center here, because this is P21O by C. P1 by C means this is the centrosymmetric space group. So if we have our XYZ, they will have an equivalent point at -x minus y minus z in a screw axis, and then this glide plane. You can see all the information that here this screw axis, the two-fold screw axis, the direction is given. It's 0, 1, 0 means it is along y, and then the glide plane is perpendicular to this with glide plane like this. So you can go through them. So these are actually very interesting to check out. Then if you do this asymmetric unit, you can see here there is only one molecule in the asymmetric unit. And then if you go for packing, then it will show you the unit cell. So you can see in the unit cell, this is the A axis, this is the B axis, this is the C axis, and you can see there are 4 molecules in the unit cell. Now till now I have not turned on any hydrogen bonding or any short contact. Now if I turn on this hydrogen bonding, it will show the hydrogen bondings in the unit cell, and I can rotate the unit cell, or I can if I want to see the unit cell down the a-axis. I will click this, so you can see here what it is showing: view down crystallographic a-axis. So if I click this, I am viewing down a-axis. You can see, so this is the a-axis, is totally perpendicular, it is going into the screen. The a-axis is going into the screen. So this right side is the b-axis, this is the c-axis. It is looking like this, but they are these two molecules, it might look to you that it is in the same plane, but it is not actually in the same plane. So to understand that, we can turn on the depth Q, then it will easy to see that this molecule is actually behind and this molecule is in front of it. So you can see, if I want to view down b-axis, it is like this. You can see that there is looks like there is some kind of the possibility of dimer formation, hydrogen bonded dimer. Then c-axis, if we view down, it is like this. So let us view down the a-axis and rotate it a bit like this, so you understand, right? Now if we click on the, so the picking mode is the expand contacts mode. Okay, so if we click on this, it will complete this bonding. You can see this forms a very nice dimer. Now if you click on this, it forms this dimer. Click on this. So from 4 molecules we have created 8 molecules, all the hydrogen bonded. So in the saccharine structure, this means that there is a hydrogen bonded dimers is there in the structure, right? So this is the Mercury software, and you can use it to draw, and then this from work you can go to publication mode, where you can take pictures like this in any desired orientation which you want, and you can use them for publication. There are some options like color by element, by symmetry equivalence, everything. So we usually stick to this. There is also this show hydrogens option. If we turn it off, then the hydrogens will not be shown. This is usually used for many complicated molecules, like for example, if there is there is a metal atom like iron or manganese or cobalt, and there is a porphyrin ring around it, so there are, it becomes very crowded. Then in such cases, sometimes the hydrogen atoms are omitted for clarity, but usually when we do organics, small molecule organic systems, we do not turn off the hydrogens. So we keep this clicked on. This select unit cell, if we do not want, we can turn it off. We have this label atoms option, where all the it shows us now all the atoms. So this, it is easier to see this if we do this reset, and for only one molecule if we want to see. So you can see the naming like this. So it is starting from here: C1, C2, C3, C4, C5, C6, C7, and then we have S1, then we have N1, and for here you can see the hydrogens are H1, H2, H3, H4 like this. If you go to measure distances, you measure the distance between these two, you can see it's 0.95, here 0.95. So if you have a close look, so all are same, they are exactly same, which means that these hydrogens were refined based on the riding model and not refined independently. Then this one, you can see it is a bit looks like that this was not based on the riding model. Okay, then we have this O1, O2, O3 like this. So you can also measure the angles here. Suppose you want to measure the angle of this this angle. So what you do is, you in the picking mode, you go to measure angles. You go to measure angles and you click the 3 points like this, and it will very nicely show you this angle is 117 degrees. Suppose you want to measure this angle, so you can click like this and it will show you that this angle is 92 degrees. So we hope you have a clear idea of this Mercury software. So so we were here on this question, right, that which among the following is used to view the molecule and packing of the molecule. So the answer is mercury. Then this 10th question, which says that which of the following parameters should be fixed before starting the data collection strategy determination. So there are some factors here. The desired resolution means the resolution which we want to achieve. So we know by now that this resolution depends upon the wavelength, and if we have copper and molybdenum, then between copper and molybdenum, if we use molybdenum, we can go to higher resolution or better resolution. Exposure time means the time for which we are exposing the X-rays. It can vary from as low as 0.1 seconds to as high as 12 seconds or 15 seconds. We use the lower exposure time when we are collecting the data at lower angles, and we use the higher exposure time when we are collecting the data at higher angles. Why? Because as we have learned from, there is a graph, right? You have to remember that when we go to higher angles, the scattering power of the atoms decreases. So we need, in order to collect the same spot, we need more more X-ray to focus, to detect that point, that suppose HKL plane or something. So exposure time is that factor, and also when we go to higher angles, so you remember Bragg's law, right? So Bragg's law means n lambda is equal to 2d sine theta. So if you are going to higher angles, which means your theta is high. If your theta is high, your sine theta is high. If your sine theta is high, then we have to follow Bragg's law, right? Then the d is low. D low means the interplanar distance is low, means at higher angles you are actually going to lesser and lesser interplanar distances, or the closer to the resolution. So we need to collect better data. So this is my desired resolution. So we learned about that, the exposure time, and then Laue class, which is either the centrosymmetric, the 11 centrosymmetric point groups, which reflects the symmetry of the diffraction space or the reciprocal lattice. And then the target redundancy means how many times the same frame will be collected. So the exposure time cannot be fixed before starting. Why? Because exposure time varies with the angle, right? So the correct option is this B option, the desired resolution, Laue class, and target redundancy. So this OLEX2 is a very useful software, and you can download the OLEX2 software from www.olex2.org, right? So this is a graphical user interface software, and it is very useful for solving the data which are collected from both the Rigaku diffractometers as well as the Bruker diffractometers. So if your data is collected on the Rigaku diffractometer, so you will end up with a folder named struct, right, which I have shown you. I have shown you this struct folder, right? And the struct folder contains all the files which you need to solve and refine your structure. So this include but not excessively. So the file name can be anything. So suppose if your initial is AB, you can give your file name like AB1 or AB2, like something like that, right? So we have this h.hkl file, which is the data file type which is used for structure, solution, and refinement packages. It contains the Miller indices, the intensities, and the error on the intensities for each reflection. So this .hkl file contains the Miller indices, intensities, and the errors on the intensities for each reflection. And so this file has been corrected for absorption. If you do absorption correction, this file will be corrected. Then the .ins file means the instruction file for use in ShellX. Then this red.sum, this file is located outside of the struct directory and it has information on the data reduction. It is this file will not be necessary for structure solution, but still it contains useful information. Then this .grl file, remember what I also showed you, this .grl file is located outside the struct directory, which contains information on how the space group was determined, which is also not necessary for structure solution, but it contains useful information. So you have to remember that this is not a complete list of files, but represents the ones which we will be using the most to solve and refine our structures. So this was all about the Rigaku data. So this was so now if we we will go to Bruker data. So for Bruker data, so what I am personally familiar with is Rigaku diffractometers and not Bruker diffractometers till now. So if your data was collected on the Bruker 2 diffractometer and integrated by the data processing software, so the files which you will get are the raw files, which is the raw data file, which contains all the reflection indices, their direction, cosines, intensities, and errors on the intensities. Then again the .hkl file, which is same for both Rigaku and Bruker, where the .hkl file is used for the structure solution and refinement. Intensity in structure solution and refinement packages contains the Miller indices, the intensities, and the errors on intensities for each reflection. And this file is often generated by the data scaling program SADABS. So then we have this .p4p file, which is the file which contains most of the experimental data, including the unit cell, the orientation matrix. This is also there if you take data using Rigaku, then also we get the p4p file. Okay, so this p4p file contains most of the experimental data, including unit cell, orientation matrix, chemical formula, morphology information, data collection parameters. Then the .abs is just the output file. And this is like again not the complete list of files, but represents the ones which we will use the most to solve. So the program which is mainly used to solve the structure is the ShellX suite of programs, and the structure solution algorithm is called the XS. Once we have obtained a solution from the XS, then we generate .res, that is the results, and the .lst, which is the output file. Structure refinement is obtained by making changes to the model obtained in the .res file, and then saving those changes as a new .ins file, and then running the refinement algorithm, which is the XL. Okay, and then this cycle is repeated until any change increases the R factor of the refinement. So this cycle, how many cycles you want to refine, so this also we can manipulate using OLX2, right? So this is the general flow chart which describes the structure, solution, and refinement procedure. So this is the gist of what we have been talking about till now. So this is looked very interesting to me, so that is why I put it here. This is all taken from the website of the if you search structure solution using OLX2, so you will get something like this. You will get this flow chart, and you can follow it to get the main idea about how it is being done, and all of it is you can do in the OLX2 only. So this OLX2 is actually a very useful software, so where in the background all these hardcore processes and these computer programs and packages and everything is running in the background, but what you get to see in the front is a very colorful and a very user friendly interface, this graphical interface, which is very colorful and user friendly and very easy to understand. So this OLX2 was built, designed like that, keeping in mind that someone who is not very used to coding and everything can also use it, and then use it very comfortably and understand it. So this is the flow chart. So another thing which is very crucial, or which crystallographers pay a lot of attention, is the R factors, this R1 factor. How less is my R factor? What should be the R factor so that I can publish the data? So that is why this is also taken from the OLX2 website, and I feel that this is a very important thing to discuss, which is why I want to discuss it here in this platform, that there is no magic R factor below which all structures become suddenly good or publishable, right? So even if your R factor is high and if you are able to explain that why it is high, then you can proceed with it. On the other hand, completely incorrect structures have been published with R factors as low as 3%, right? That is why it is very important not to follow the R factor blindly, and you have to use your brains and intuition when dealing with these R factors. So if your data has high signal to noise ratio, that is high I by C, this, so high I by C, this means high signal to noise ratio and low RINT. RINT means the R internal, and your R factor is still high, like greater than 10%, then something is probably wrong. So if your model makes no sense but your R factor is low, then it means that there is something wrong, okay, with the structure. So, and then when you are saying that you have completed a structure, or when calling that a structure is done, do not focus on getting the lowest R factor. So this is very, very important, that do not focus on getting the lowest R factor. So you have to make sure that your model is making chemical sense. Make sure that there are no unexplained errors in the refinement, and make sure you did not miss symmetry or grid. And then most researchers focus only on the final R value of the refinement to judge the quality and completeness. So this is not a very good thing, and R factor, so this is the final verdict, that R factor alone is a poor way to judge the quality of a structure. So that is all for today. So if you have any questions, so please feel free to post in this ask a question tab, and please also you can let me know, okay, in my email ID. So thank you.